Hello. This is Josh with another data structures assignment, the third one about Btrees. When you unpack the zip file, you shall see main.cpp and the make file in there. To compile it, all you got to do is type make, and then you can run it with /bs btrees. Btree, excuse me. And then it'll prompt you to construct a 5-way B tree by giving it an n. And for my n, if I do anything less than 400, it's going to be like, it's got to be 400. Even if I do a negative number, it's going to be like, got to be 400. So I'm going to do 435, 7. Then after you get all of the keys that it searches for, it sort of skips to the end, but it generates a B tree out of random elements from the range that we were given. And then we were supposed to search those elements in that B tree, and I returned them in this sort of grid right here. So so out of the 437 elements that are in range, which is 437 to 890 or something, it grabbed 139. So that's less than the average. Usually you're going to get at least a third if you just randomly get it, but this time we got a little bit less, so a little bit under a third right there. So this is not required, but I thought having the stats were interesting, seeing like the percentage of the keys returned out of the total. So the returned keys, and of course they're going to be between 437 and 2 times 437. So, and then it lists all the keys here if you want to like keep track of them, I guess. But yeah, so that displays all the keys. And if you wanted to compile it and run it at the same time, you could do make run. And then it immediately just compiles and runs to enter n to construct a 5-way B tree. I'm like, all right, what about just 400 bare minimum? So there we go. All those keys. Now, of course, the lower you get, the less keys you're going to grab. So there were only 134, a little bit above a third, but very slightly, only about 2/1000ths above a third. So yeah, so everything from 400 to 799, n to 2n, all the stuff in this range. These are the keys in our B trees that we search for. So I'm going to show you. That's how you run the thing. This is what's in the thing. So if I go into main.cpp, my B tree is not a class, it is a struct. I thought it would be simple just to make it a struct, and I have a reference to the parent, because doing all of the checks when I'm adding things, I have a parent reference there, so it's easier to make sure I know where I am on the tree and what's going on. I have vectors for its values and its children, and its children, keys are going to be always +1 more than its values if it does have children. So, and I use the algorithm sort and swap to make it easier to just run the code. So it's just sorting the vector and then swapping 2 values together is the only time I use sort. So the biggest thing, hardest thing about this is the insert value. If you can insert a value into your B tree correctly, it'll be fine. So I have it down into like 4 chunks. So this if statement is the first chunk, where this is if the head does have children, then we're not supposed to add one to add this new value to the head. We're instead going to try to add it to one of the children. So we check where we're supposed to add it. We're supposed to check which children we're supposed to go down in which, depending on what the value is. So we find the right key in that children vector and we go down it. So just less than equivalent, then we set it there, or we go down there. And in the for loop, I'm only checking for the left. I'm only checking if it's less than to go down left, or if it is equivalent, then we're supposed to make one down there. And then for the last child, because there's going to be +1 child, I do another if statement at the end of the for loop. So I do like check, 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 and then I go down. So, I just realized that I could actually just set this to greater than or equal to, and it would have the exact same effect. So yeah. Anyway, if we go to then we go down to here, and then so if this isn't true, it doesn't have children, we're just going to add it inside of the head. So if we do, we're just going to add to the head, just like that, and then we sort it so that we make sure so this pushes it at the end of the values, so then you got to sort the values to make sure it works. But if we now have our size is 5, so if it's less than 5, we can end the function right here. But if the head now has 5 nodes, then we can't leave it like that. That's not a proper 5-way B-tree, so we got to do some more complicated stuff. So next we check if the head does have a parent, and if it does have a parent, then we're going to check if the parent has space. So if it does have a parent, but it has like 4 values, then we can't put in another value in there. So I'm gonna skip this for now and come back to it. This is the parent doesn't exist line of logic. So if the parent doesn't exist, this means that we're in our master node and we need to split this node into basically into 3 nodes. So the node that we're in right now is going to retain the median value, but we're going to have the 2 values on each side of this node become child nodes and become children to this current node. So we do that by left child, right child, and then we just make sure we push it in the right order. I know these are hard coded, but it just seemed I really don't want to go to head values dot size -1 or head size dot values. I just did that. And then we erase the values with the erase function, because that's another great thing about vectors, that you can just erase more than one value at once specifically. So that's pretty nice. And then we make sure we connect everything together, make the children's parent node link to this current node, and we take this current node and add the children to it. And then, so let's go back. That was the easier section, but honestly, the hardest section is right here, where if it's not the root node, if it does have a parent, but that parent doesn't have space, we need to do this new right child business. So basically, the current node has 5 elements, which is bad. We're going to keep the front 2 elements, push the middle element back to its parent because there's space, and then we're going to create a new node with the last 2 elements and make it a sibling to this current node. So that's why we need that reference to the parent. So we need to push this we need to make this new right child node parent the same as our parent, or this current node's parent. So we just get the last 2 elements and then push them into the right child, and then we make sure we have the right child sorted correctly. So it inputs it in the opposite way. So it's like the last one and then the next to last one after we pop it. So it's in the incorrect order. So if we just swap those 2, then it solves the problem. Don't need to do a sorting algorithm. We can just swap right there. And for do the parent. And then we do the pushed up value. We save it to, this is the value which is the median in the current node, and it's now the last, after this business is now the last value in values for the current node. So we push it back up and we make sure we delete it. So now our node is right where it needs to be. The head only has 2 values in it, and but we do need to make sure we sort the parent, because we just pushed a new thing into the parent. We got to sort it. So we do a sort, pretty simple. And then we got to do some iterator business, because I need to make sure I put the child node for this new right child in the right spot. So an iterator is not exactly an integer. It's a C++ thing that like a values.end is an iterator. It's not the exact. So like this is the beginning. This is a reference to the beginning, and this is a reference to the end of values. So with the iterator, we got to grab. So we have to find where the pushed up value is after we sorted it, because I don't know. It could be. I'm not exactly sure where it could be. It's supposed to be like either in the second or third spots in values. So we just got to make sure we know exactly where it is. So we sort it, and then we search for it using the find algorithm. When we find it, we then store its index as the distance from the beginning to where this iterator is. So this iterator starts at the beginning. So if we take the distance from the found value from the beginning, this is the found value iterator, found value, and then we just take the distance between the begin and the iterator, we'll find the actual index. And then with that index, we can add it to the children. So this is not values, this is the children, this is the keys to the child nodes. And we add index to the iterator right here at children, and that'll give us at the right spot. Well, not exactly. Right spot +1. This is the right spot, and we add 1 to it, and then we can safely add the new child. So it's pretty complicated. This is the longest part of the entire process, but after this was working, everything else fell into place. So there you go. Toughest spot right here is when it does have a parent, but and there is space, so you got to push it back up. So yeah, that's annoying, but everything's a lot easier. These are helper functions to print out the values. To print out the tree itself, but it's really disgusting when you try to print out the tree when it has more than 3 layers. So I just don't, and it's not supposed to happen in the program anyway, so I don't do it. But yeah, it's just some for loops going through the child nodes, the head node, the child nodes, and then printing them out. And then I even get to 3 deep down to a triple loop. So like we're at level 3. So if the top's level 0, this is level 3. So it goes like 4 layers down. Yeah, it pretty stinks. Anyway, so this is the find value. This is the other thing that's very important, but fairly simple. We start with the root node and then the value that we're trying to find, and it's a Boolean. We're trying to see if it's in there or not. So we just go through and then we check if, if where we are in the for loop is greater than the value we're searching for, that means we need to go to the left. So we go down the left, we go through, go through the find value, down the initial child, or at least the child key, off of the values, and then go down there. Sort of like before, we can't go right in this for loop. We only go right for that like farthest right key. If we reach the end of the for loop and we check, okay, if, and also there's this if statement here so that I don't get a seg fault, making sure that that if our current node does have children, I can go down. So if it does have children and we're able to access the back, and then we know that we're supposed to go right because we've checked everything and all of the values are not greater than, this value is greater than all of the values inside the head node, so we're going to go right. If we do find the value, where we're going through the value and we actually find one of the values inside of this node is equal to the value we're searching for, we're like, boom, we found it. So we can return true and back up through all of the recursive calls. But if we have checked all of the left paths and we've gone the right path and all of it comes back negative, then we return false. So if we go through all of this and we can't find true, then we're going to return false. So nothing's in there. And then we get to the main and we construct the B-tree. Here's our head, which is the B-tree. And then I just have n to 10 as an integer, and then I make sure that you get the user input, checking to make sure, using the do while. I love do whiles for user input because you can check the user input after the fact. So we're like, please enter to construct 5-way tree, and if they don't put in the right thing, we're like, it's got to be greater than 400, then repeat because it's not greater than or equal to 400. I created a list of integers which are simply I, so it goes from 0 all the way up to 3 times whatever n is. So this is just an ordered list of integers inside of a array. And then to get the random integers without getting any repeats, I take this list of integers and I will find a random spot inside of the list of integers, which is 3 times n. And then I will make sure, so this while loop just makes sure I'm skipping spots that I've already taken. So, and I set a spot that I've taken a -1. So if it's -1, we're going to increment it. And if we increment to the very end of the array, which is this if statement, we're going to reset back to 0. So that way I don't save any spot that's already been taken. I skip it and go to the next spot. And when I do take a spot, set int list of the index that I want into the random list, and I set it to be -1. So, and then random list is only n elements. We're only searching, we are making our B tree out of n elements. So that's what we got to do. And we then, so this is actually creating the B tree. So we use that really complicated function, insert value, and I give it the head. And then I pass it every element in random list, which is now a random list of integers. From the range 0 to 3n, which we have just done up here. And then I search for the correct, I search for all of the keys in between n and 2n, and storing them in an integer array called found values. And then the counters to keep track of how many actual elements are in the array that are in the right range. So I call find value, and it does its recursive stuff. And if it's true, then we set the counter to be I, and we set the found value to be whatever I is. So I is actually going through each key that we're searching for. So I starts at n and goes up all the way up to 2 times n. So that's all of the range that we need. making sure that we grab everything inside of that range. And we set it to I, and then we increment the counter. Because the counter is the thing that actually keeps track of how many values there are. The length of this array is not how many values we found. That's just potentially how many values we could find. Potentially it could be 100%, so it would be n, but that's never the case. So, and then while I'm doing this, I also print out what key I found visually, and if I don't, I print out a period. So that's how you get that little graph that shows that sort of grid that shows which elements I did find and which elements I didn't find. So the elements I didn't find are periods, and the elements I did find, they're actually there. So and then we indicate the percentage of range n by 2n. This is unimportant, but it's what I put there so I can see the actual ratio of the found elements compared to the search size, which is n. And then it displays those elements and the keys that we did find in counter. So the amount of both. So that's pretty cool. And then I return the keys. Just want to make sure I, accurately follow the instructions. I also display the keys by these are the return keys, and then I just list them all out like that. So, and then we finally reach the end, and we have reached the end of this journey with me. So thank you very much for coming along, and I hope you give me a good grade. Thank you very much.